Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review Pythagoras' theorem. So it concerns right-angled triangles like this, triangles where the largest angle is a right angle. We call A and B the lengths of the two shortest sides, and C is the length of the hypotenuse, which is the longest side, always facing the right angle. Turns out in any triangle, the longest side always faces the largest angle, the shortest side always faces the smallest angle. So Pythagoras' theorem says that a squared plus b squared equals c squared. Shorter side squared plus shorter side squared equals longer side squared. So we can rearrange this equation to get these two here. We use this one when we're finding c, the longest side. We use this one when we're finding a shorter side. So you plus when you're finding a longer side and minus when you're finding a shorter side. So let's apply Pythagoras' theorem to this question here. We have a right-angled triangle. We're finding the longest side. We use this formula here. So it doesn't matter whether you call it x, c, whatever. So Pythagoras' theorem just says that longest side equals square root of shorter side squared plus shorter side squared, and then you can put that straight in your calculator and you get 25. So in the red triangle over here, we're finding a shorter side, so we use this formula here. So Pythagoras' theorem says that the shorter side is equal to the square root of longer side squared minus shorter side squared. We subtracted because we're finding a shorter side. So the exact answer here is the square root of 5. Because 5 is not a perfect square, this is an irrational answer. This is the exact answer, or if you round it, it's about 2.236. So just be aware whether the question is asking you for an exact answer or a rounded answer. So let's look at this one here. Here we have a right-angled isosceles triangle because it has two lengths of equal side, and we're told the hypotenuse is 1. So we can't use either of these formula because we have two unknown sides. But what we do know is that a squared plus a squared, shorter side squared plus shorter side squared, equals longer side squared. Well, a squared plus a squared is just 2a squared. So we've got 2a squared equals 1. Divide each side by 2. And then you square root each side. A is the square root of a half, or 1 over root 2. That's the exact answer. And as a decimal, it's about 0.7. All right, let's now look at some harder questions. So we're going to find the length of x in each of these triangles using Pythagoras' theorem. So for this first one, we know that Pythagoras' theorem says that shorter side squared plus shorter side squared equals longer side squared. So for the longer side, we want to square the whole thing. See, we actually get x squared plus 10 squared is 100 equals 9x squared. 3x all squared is 9x squared. All right, how do we solve that? Well, we want to get the x's all in one spot, so I'm going to move this x squared over there by subtracting it. I get 100 equals 8x squared. Divide each side by 8, you get 12.5. And so the exact answer here is x equals the square root of 12.5. So if you round it, it's about 3.54. All right, let's now try this one. So again, we use Pythagoras' theorem that tells us that shorter side squared plus shorter side squared equals longer side squared. So for the longer side squared, we're going to have to use what we know about expanding brackets. So 56 squared gives us 3136. Now when I'm expanding the brackets, when you have perfect binomial square, you square the first, you square the second, so 32 squared is 1024, and in the middle is twice the product. 2 times 32 times x gives us 64x, and the last term's always positive. So what we can do here is we can cross out x squared from both sides. Essentially, I've subtracted x squared from both sides. So I now have 3136 equals 64x plus 1024. I'm going to subtract 1000. I get 2112 equals 64x. So now I simply divide each side by 64, I get x equals 33, and we're done. Let's now look at Pythagoras in 3D. So by Pythagoras in 3D, I'm talking about when you're finding a distance in 3 dimensions. So we use this formula here, x squared plus y squared plus z squared, where they're the 3 lengths. So let's say I want to find the 3-dimensional distance to go from this bottom corner up to here. It's helpful to think of it as being the longest stick that could fit inside a rectangular prism. So I know my drawing's not great, but this is like starting down here and it's going up diagonally. So it may look a bit complicated, but we simply use this formula here. X, Y, and Z are the lengths. It doesn't matter which you call X, which you call Y, which you call Z. Simply, L, the length, is just going to be the square root of 6 squared plus 8 squared plus 10 squared. So the exact length is the square root of 200, and the approximate or rounded length is about 14.14. And we just write U for units since we didn't know them. All right, let's now look at Pythagoras in area. So Pythagoras can be very useful when we need to calculate areas, but there are certain side lengths we don't know. So let's look at this triangle here. I want to calculate its area, but the area of a triangle is base times perpendicular height divided by 2. H, when it comes into a formula in measurement, always means perpendicular height. So it's actually referring to this perpendicular height here. Problem is I don't know what H is, but I can use Pythagoras to find it. So it turns out if the original triangle is isosceles or equilateral, you can divide it into 2 congruent right-angled triangles. And it's important that they're congruent because it means that this length here will be 8. We know that this side here is 18. So we simply have that H is equal to the square root of 18 squared minus 8 squared. So that equals the square root of 260. Now I want to leave my answer as root 260. That's the exact answer. Why is that? Because I'm now going to use this in a subsequent step. I'm going to use it in my next calculation, so I want it to be exact. So the area of this triangle is going to be the base of the triangle, which is 16, times the perpendicular height divided by 2. And if you put that straight in your calculator, you get about 129 units squared. So I wanted to use root 260 rather than have it rounded because that would introduce an inaccuracy at this step. All right, let's now look at this shape here, a trapezium. So the formula for area of a trapezium is h over 2a plus b. So a and b refer to the 2 parallel sides. H, once again, is the perpendicular height. So it's actually this height here. So I can't really find the area without knowing this, but fortunately Pythagoras will allow me to find it. So we need to draw a right-angled triangle somewhere. You see, if it's 73 from here to here and 150 from here all the way there, this length here must be 150 minus 73, which is 77. So I can draw a right-angled triangle here to find H, because this distance here will be the same as the distance there, because these two lines are parallel. So let's use Pythagoras' theorem. So we're finding a shorter side again, so we minus square root of 85 squared minus 77 squared, which gives us exactly 36. Now that I have the perpendicular height, I can easily find the area. It will just be perpendicular height divided 2 multiplied by the sum of the 2 parallel sides. And I get 4,014. So once again, because I don't know the units, I'll just write u squared. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.